So recall if I have a spatially varying magnetic field, right, but time independent. Independent field. Right? Then if I have a loop moving at some velocity v, right, because of the Lorentz force, right, there is the line integral of the Lorentz force along the loop is non-zero, right? And this is the EMF of that loop. If this is a inductor, then current will flow, and this is given by, we analyzed this last time, it's given by the rate of change of the flux through that loop. Okay, and you can generalize this into arbitrary shape and arbitrary loop and arbitrary velocity, and it's still the same as long as moving in a time independent field. Okay, in particular for this loop, say if I have V1 over here, just to be specific for the purpose of the example later on, it is V2, right? Then the change in the flux here, okay, I'm defining positive direction that way. Right? It's important to know your directions and your sense when we talk about magnetostatic, right? The positive sense, I guess, counterclockwise, and this is going to be equal to minus B1 minus B2 omega, not omega, W. W is the width of the loop, right? Times the velocity times B2. Okay. This is for this rectilinear case. Now, from the frame of, I guess in this case, this is an E- frame, because it's in the lab, but what if we jump onto the frame that that Jarvi is sitting on the bed, right? The prime, sitting in the loop. Right? Then what does it see? If a loop like this, right, it's stationary now. But this B field, this time varying B field, is receding in that opposite direction, the velocity v, right? Okay, so you develop, then you from the transformation of field, you know that you develop an E field in this direction. This is all in the prime frame, right? In the prime frame. Right, and there's an E field in this direction, right, and it's given by, so you just go to the formula, but I'm just calculating the magnitude, this is V times V, right? Okay, and V is the velocity of the loop, and V is the B field in the home frame, okay, in the lab frame. So in this case here, then if I calculate the line integral of E prime, L prime, it's not going to be zero, right? In fact, it's going to be equal to, it's going to be E1 prime times the width, right? Because I'm still doing the same sense, positive direction like that, and there is an E1 here, there is an E2 prime here, in that direction, right? So this is going to be equal to E1 prime minus E2 prime times W, right? That's the line integral, okay? And then I'll substitute this equation into this expression. I'll get something like V1 minus V2 times V times W, right? Okay? And this is just equal to exactly what was that? That is that the expression. That's the rate of change of the flux, right? Okay. In this case, I'm not worried so much about I'm considering a small velocity movement, so gamma is close to 1. But I don't have to worry about factor of gamma anywhere anymore. And that's the EMF, right?
Is your E2 is the on the loop? Is it that way? For
E2,
both?
no, E1. So P is that way, right? P is all upward,
Yeah.
and in this case, especially varying is diminishing
Yeah.
the x direction, right? And then it's receding in that direction, right? So according to E prime, right, there is an E field going in this direction, in the minus y direction. Right?
For all over, or just
all
on the
over,
loop?
all over.
So it's not on the line.
No, it's everywhere.
Okay.
Yeah. Everywhere there's a B field, there's an E field. Remember we talked about the special frame. In a special frame where E field is 0, right? Then in the moving frame, right? Then there is an E field that is just V cross B.
Yeah.
And that's what I'm doing, V cross B, right? There is V. This loop was moving in that direction with velocity V, right? So V cross B, you get an E field.
Okay.
In the minus y direction.
And for the Lorentz force, can you substitute any force, or is that why the E is equal to?
No.
Or,
if I have a loop moving in a magnetic field, then there is a Lorentz force,
Yeah.
and this Lorentz force is creating this electromagnetic electromotive force around the loop, and it's given by that integral, right? It's non-zero. There's moving charges in that conductor. Okay?
Yeah.
Right? And the electromotive force is given by the rate of change of the flux with the minus sign, right? That comes from the Lenz law. The minus signs come from Lenz law. Okay. Lenz law says, just to remind you, because Lenz law is important when you're trying to solve problems, right? So what happened is the EMF is such that the induced current generated is such a way that it actually opposes changes in the flux. And the next example will show more carefully or more clearly what I meant. Is this clear so far? So what happened is I'm analyzing the whole situation up there. Charlie is here now, and Charlie is sitting on the loop, right? Okay. And then from Charlie's point of view, there is an E field. And this E field is creating a non-zero line integral. Right. Remember in electrostatic, this is 0. But that's no longer the case here. Right. And we'll explore more. Okay. But any questions so far here? Right.
So the way that you define the direction that you're doing the line integral, does that mean that if the line integral is positive, then the EMF makes the current go that way?
Yes. So you have to define your sense, right? Anytime when you get a negative number in your calculation, then things are going in the opposite sense. So in this case here, hopefully I've done everything nicely so that there is no negative number, right? I mean, the way I'm drawing it is the magnetic field is diminishing with space, that direction, right? So by Lenz law, I will create a current, right? The current here, the induced current generated by the EMF, right, is such that it will produce a P field upward, induced P field, right? To counteract the loss in flux. Okay? So let's apply this to an example. Remember, this is one of those rare cases that there's a perfect timing in homework and lecture. Right? Yesterday we talked about this infinite solenoid, semi-infinite solenoid. Right? And we know inside there's a V that is in C direction, by the way, and is equal to mu naught n times I, right? Okay? So let's do an experiment. So there's a B field everywhere here, and I think most of you in discussion yesterday, you'll find that the B field actually here, at tip here is still axial, is half of mu naught n I, and over here the B field is actually completely along the xy plane, right? We showed that yesterday. What else we showed? In general, things kind of look like that, right? Okay. So now I drop a loop, right? There's a loop here,
Isn't it?
right? And it's falling at some velocity v. Okay. And forget gravity. Since you're doing this in space, I don't have to worry about changing speed, right? The speed is constant, falling into the solid line. So what happens? How do we analyze this situation? So first of all, where is the Lorentz force? If I have this loop, right? Velocity is that way, right? If I look at the axial B field, the axial component of the B field, phi cross B is 0. Right? It's not going to create electromotive force, right? So this will contribute to 0 EMF, right? Because it doesn't have any Lorentz force, right? Is this clear? So the reason that there is a Lorentz force, in this case, I'm just going backward, we know there is a Lorentz force, is because in this semi-infinite case of a solenoid, the B field is not exactly in the same direction. The B field actually has a radial component, right? Because this thing is like flattening out, right? So there is a B field in the radial direction. Right, this is right again, there's a B field radial, right? And there's a velocity like that going downward, it's falling, right? So phi cross B, right, will give you Lorentz force that way, right? In this case, phi cross B will give you Lorentz force this way, right? And that's what's giving you the EMF, that the integral of this Fm along the loop is the EMF. Right? And you can show actually that this is, we're not going to do it here in class, but now that you know how to solve this problem from the homework, then you can show that in the end this is equal to also minus change of flux per unit time, right? And maybe we'll show it at the end of class, but I'm not sure about to that. Okay. So now, how about from a point of view of Charlie, right? If Charlie is falling with the loop, right? Then what he sees is something else, right? But I don't want to belabor the point. Just get the idea. With the loop, this is Charlie, and this is moving down. Okay. Again, actually this is kind of important, right? Again, in the home frame of Iman, right? The B field is parallel. V is parallel to V. Right? And the B perpendicular is 0. Right? And there is no E field. It's 0 everywhere. This is according to Iman. Right? Okay? So what happened to at least inside, but not outside, right? Outside, this is non-zero. Is that what I did? I have all this transformation, but get the idea, right? What happened is, if this thing is falling with velocity v, right? The part of the B field that leads to a circulating B field, right? We want this, right? In Charlie's frame. This comes from the gamma V plus B. We say gamma equals to 1. Right? So again, the B comes from the B that is actually perpendicular. Okay. The actual B field doesn't contribute to a circulating E field in Charlie's frame. And that is what gives rise to an EMF, according to Charlie. Right? Because of this flaring of the B field, they create a circulating E field. Okay. So I will go back to this again to become more clear. But is this the whole story? Again, is this the whole story? Because where were we? Right? Because we found this, right? We found that. It's also equal to the rate of change of the flux. Right? Are we done? Turns out we are not. Let's consider an example. Now let's look at this. This is the thing I want. Right? Can I erase this? We've done it this way. So how about if I instead of being at the top of a semi-infinite solenoid, I'm actually deep inside. And forward. Okay. Okay. Then there is no EMF. Because there is no Lorentz force here. The B field is completely axial. Right? There is no radial component of the B field. So the B field is along the velocity direction. It cannot create an EMF. Right? Okay. Hopefully I'm not missing any argument. Just want to make sure. B field is 0. I can change the current, right? I can have a varying current. You know this from maybe your high school physics, right? I vary with time. Right? Okay. But still, there is no Lorentz force, right? Lorentz force is still 0. Okay. This is where I want to, this is where I want to talk about this equation, right? Inside, inside the solenoid. This is all true, right? This is 0, right? So in that case, then this is also then equal to, because this is V parallel, right? This is also equal to 0 because V perpendicular is 0, right? And V parallel is 0, right? According to Charlie, there is no V. Right? Okay? And the B field is the same. Like the only B field that's there is the B perpendicular, or B parallel, right? It's always B parallel. And B perpendicular is 0. Okay? Right. So something is still missing, right? And what's even weirder is this, right? Of course, telling the story completely backward. What's weirder is how about outside? If I make a loop outside, it's an infinite solenoid, right? So the B field outside is identical to 0, right? There is nothing, no perpendicular, no parallel component, current can be changing, there is no P field. There is no P field, you know, you get current moving in that loop, right? So you get EMF. I mean, it looks like from this consideration, right? It looks like the loop is disconnected from the solenoid, right? There is no physical connection whatsoever between the solenoid and the loop, right? The P field is completely confined, right? So do we have EMF, right? So what do you guys think?
Seems like it would be no.
Yeah, you can take that back. But before, this is what the effective potential comes in. Right? You think it's useless for a while, it was useful, calculated by standard law. But recall the effective potential. Solenoid E field is driven by the curl A, right? And we can choose a particular gauge of A, right? So the divergence of A is equal to 0, right? In that case, we found for this particular story for this particular case of a solenoid that the line integral of A in L close loop, right, is equal to the flux of V dA through that surface of the loop. Right? And we did this lecture and we found that the vector potential outside by just doing this integral, right, is equal to V naught let's call it radius, let's call it A, right? V naught A squared over 2R in the V direction.
Wait, what is
That's a vector potential, right? Recall our lectures a week or 2 weeks ago.
I mean, like the little bit.
Oh, the little a is the little a is the radius of the solenoid.
Oh, and then R is the radius of the loop.
Yeah, R is the radius of the loop. Okay, and inside we also find that inside you can do the same thing, right? If you look at your notes from all lectures, this is given by V naught R over 2, also in the same direction, right? And V naught is mu naught and I. I don't know why I did naught, but there's I naught here. Okay? So the vector potential is non-zero outside, right? And just remember this equation for now. Right?
So R, what is R? Is that the loop? Is the loop outside the solenoid?
If I want to solve the vector potential everywhere, this problem has cylindrical symmetry. Right? It looks the same as I wrote it around the solenoid.
So it's not the loop from over here?
It is. It's the same loop.
Same loop.
Same loop.
It's just outside.
It's outside and
Okay.
inside. Right? I'm calculating the vector potential everywhere.
Okay.
Right? Just so that you recall from lectures, 3 or 4 lectures ago. Right? So the vector potential is non-zero outside. It is A. It goes like this. 1 with R, and then this is with S bar. Okay? Here. So let's go back to Charlie's frame. Right? In Charlie's frame, where are we? I want to read this one, and then we can step up one. Okay, this is in the image frame. We have that, right? In Charlie's frame, get dl, right, is equal to minus flux dt, right? Okay. If this is the change of flux is minus dt, this is an integral over any loop, right? This is the loop that Charlie saw, right? Over the surface of dA, all with the prime, right? This is what Charlie saws. Okay. So I'm going to do this completely backwards from Purcell, right? And we're going to get it. Of course, it's already solved, and this before bottom is fine, right? You have this equation, and you have that equation, right? Forget about the prime in this case. So from here on, Charlie's is the ground frame, is the lab frame. Right? It's back in the lab. So this I'm going to be, well, I don't want to erase, but we'll erase all the prime, right? Let's consider a stationary frame which Charlie with the lab, right? If you look, compare these two equations, it's very similar, right? You see this? Right? Maybe I can just do it that, right? So if I substitute this, right? The line integral of d dl is equal to minus dt of the flux. But let me write the flux in terms of the line integral of the vector potential. Okay. So then what you have here, and this is true for any loop and any surface, right? Okay. In particular, if you want, so that we not any surface here, right? So that this is true over a surface. You can also write this from Stokes' theorem. You can write it as a curl of E dA over a surface is equal to minus ddt of curl of A. Yeah. Okay. So if you look at the form of this equation, then then you can conjecture that maybe you can actually write E as minus derivative of A with respect to T. Okay. And if you do that, okay, if you think that is correct, right? Then what are we here? Can I erase something? If this is true, right? So far, this is just a conjecture, right? And if that is true, right, then okay, then I can, if I take the curl of this, the curl of E, then it becomes the curl of dA T, right? Okay, and I can change the order of the differentiation. Then the curl of E becomes minus ddt, the curl of A, right? And this is just equal to minus dt. And let me write it again because this is important. line integral of EDL is equal to minus the T of EDA. Right? And this is Faraday's law. Sorry?
In the lab frame?
This is in the lab. This is general.
Okay.
This is general.
So any-
Basically, I'm going to summarize it, yes. So after going back and forth between frames, and I get confused, and I'm the one who's actually giving the presentation, the audience will get even more confused. Not because I understand it better, just it's always that. So, Faraday's law, I think I wrote it down somewhere. So any closed curve, if you have any closed curve, okay, stationary, and the time dependent, and or spatially varying, field, right? Then you always have to have the line integral of E, the L, is equal to minus the E, or to write it in the differential form, the curve of E is equal to minus
So, were you initially brought into consideration of this, which is with the loop outside the solenoid?
Yes,
It's
yes.
still not in a time-dependent or spatially varying B field, because B was 0 outside the solenoid.
But the A is not zero outside the solenoid. That's the idea. So this is why it was not enough to just look at the Lorentz force by itself, right? And it's also a mistake, because a lot of people have this misconception. Well, Purcell showed that magnetic field is an effect of it's a relativistic effect of electric field. That's actually not true, right? There are two sides of the same coin. As you see, this discussion of going back and forth between the two frames, right, looking at Lorentz force is not enough, right? In particular, the consideration of the field outside of the solenoid, when the P field is zero, right? I brought in vector potential, right, to tie the knot, and then leads to Faraday's law, right? Purcell did it differently. Purcell did it differently by considering exactly, actually, it was a consideration of Einstein. Einstein, in his paper in 1905 on the effective dynamics of moving bodies, the paper on special relativity, talked about that particular three example. You should read it in Purcell, right? Basically what he has, right? And they're both equally valid. I have a solenoid, in this case a finite solenoid. Right? So it generates a B field like that, right? So it's, the B field is diminishing the distance. And if I have a loop moving its velocity v, right? According to the solenoid, there is a Lorentz force, right? Because the loop is moving away, and it interacted with the B field, it creates an EMF, right? This is U, right? This is Iman, and this is Charlie. Charlie is back moving again, right? But according to Charlie, the solenoid is moving, right? So there is a transverse electric field that he sees, and that creates an EMF inside his loop, right? Okay. But that's not general enough, because what you're considering is basically, the difference between these two inertial frames, right, relative to one another. And you have to plot in one extra example, which is the example number 3 in Purcell, is you vary the current. Suppose this is stationary, and you vary the current. Right? When you vary the current, right? And also he brought, which is something necessary too, although it's not quite clear, the argument is not that clean because what happened is he's making an identification between a receding solenoid and a diminishing current. Right? Suppose you put a current, right? This is what he said. You put a current. So it's a current, a black current that is permeable to magnetic field. Right? So Charlie's here cannot see Iman. Right? So in one case, the Iman is residual with the solenoid. Right? So there is a B field that leads to there's a B field here that leads to an E field, and then there's an EMF according to Charlie, right? Okay, because the B field, this thing is receding, right? But the same thing can happen instead of EMF moving away. EMF can just change the current, right? And because Charlie cannot see what EMF is doing, right? In theory, you should get the same result. Right? And from that consideration, he actually arrived also at this. Right? So these are two avenues. One is more experimental, right? In the spirit of the past, that's how it's always been done, right? You start an experiment and motivate the theory. But nowadays people do things the other way, right? They actually look for theoretical consideration and make hypotheses. Oh, well, maybe this is a new theory, right? So that's like the other route. So I look at the vector potential, right? And try to make an identification between this formula, right? Between the formula here and the formula there, right? And conjecture that, well, what if E is equal to the time derivative of the vector potential? And then arrive at the Faraday's law, and then prove it with experiment.
So basically, the problem with the way we were looking at it before was that it didn't have any term for changing I.
Yes,
it was invariant in
yes.
that.
Correct.
So that the prediction there
So it's not
wasn't
completely-
necessarily wrong, because if you have an infinite solenoid and the loop outside it, it will be zero.
The current is not changing. You're
Right.
right. If the current is just constant,
Right.
I mean, there is no new physics here, right? If the current is constant, then there is a constant B field, right? And if you start with if you start with the experimental derivation of Faraday's law, right? And you say, well, there is no changing flux,
Right.
therefore there is no EMF, right? But on the other side of the coin, though, right, you have a changing flux. If all there is to it is just this relativistic transformation between Lorentz force and Faraday's law, quote unquote, then if I have a changing current here, right, you will not predict that, well, is there an EMF there? Right? Because B field is outside, it's zero. Right? And the B field is confined to the solenoid. So there is no interaction between the solenoid and the loop. How can the loop knows? Right? How can the loop knows that there is a changing B field? Right? So there is something non-local about magnetic field because the vector potential is non-local.
Oh, okay. So the loop would know.
The loop would know because of the vector potential. Right? That's the lesson here, right? So at the end of the day, we still have Faraday's law, right? And at the end of the day, this is it, right? This is a general statement that at the end of the day, after you have all the other Maxwell equations, is relativistically invariant. Okay? This is the first step. The first step is this equation. Okay? This is a modification to the electrostatic statement. You use the curl of E is equal to 0. Right? Faraday modified, right? But Maxwell, after Faraday, modified that the curl of E is the time derivative of B. Right? And it's an experimental statement that got distilled into this equation. Right? But we are doing it backward. We're doing it in a roundabout way because we already talked about vector potential. Okay? Then, this is how theories generate theory nowadays, right? They make conjectures, right? So here, the same thing. Suppose you don't know any of these Faraday's experiments. you can make a conjecture that, well, looking at this and looking at that, right, the equation looks similar, and in fact it's exactly the same if electric field is the time derivative of vector potential. But I'm going in a circle here because at the end of the day, everything is consistent. Is this clear so far? Let's talk about okay, so we're done. We're done with the theoretical consideration. Now we can apply. Question? Is this confusing, by the way? Tell us.
Can you explain one more time why the EMF is 0 if the loop is inside the solenoid?
If the loop is inside. No, it's not 0.
Okay, it's not 0.
Right. It's not 0. But everything that we did by looking at the relativity transformation doesn't show you that. Right? Either you actually have to go to experiment, right? And then deduce from it, like Faraday did, Faraday and Maxwell did, right? Or we already have clues, right? We have a lot of clues because we're doing, we have a model approach, right? Well, we know about vector potential. In fact, Maxwell didn't know about vector potential, right? Vector potential is a latter development. We know about vector potential, and you're just making some conjecture here, right? Because at some point, you have to introduce something new. Faraday introduced something new. That's my point, right? It's not that relativity solves everything. You have electrostatic and you have relativity, and then you're done. No, right? Faraday introduced something new, right? And that is this equation. Okay. Question.
Why isn't that Faraday's law? Why is that Faraday's
This is
law?
Faraday's law.
I thought that was Faraday's law.
It's the
Oh,
same.
that's the same
It's the
thing.
same.
Even if there's an error.
It's the same.
Okay.
This is the
Yep.
integral form. This is the differential form. Okay. So let's do an example. So from here on, the world is your oyster as far as AC circuits and inductance and all that. But before we move into that chapter, chapter 8, I want to introduce the concept of inductance. But before we do that, there is something interesting that I want to point out about the homework. Again, bring it backward, right? This is homework number, what was that?
Which problem?
By the way, any question on this? Let's do this right. I talked a lot about this yesterday, right? In particular, we find that the field here is straight, right? And here is half of mu naught and I, okay? And I didn't have time to look into it, but in part C of the problem, or part C of the problem, you actually can show anywhere here, anywhere on the top of the solenoid, and E, right? The axial E field, right? The axial E field. Of course, the E field is actually, like that, right? Flowering out, right? But the axial is actually half mu naught and I. Right? Except that it has a radial component that depends on position. Okay? Okay? So, we don't know how to calculate this. Right? I mean, you can, right? You have all the machinery that's difficult. And then at the end of the day, it's nothing more than you have proven that you know how to integrate, right? But I'm not that impressed if you know how to integrate. No, actually, I am impressed. You know how to integrate, I don't know how to integrate. I forgot a lot of my integration skill. Actually, I just didn't know. But Biot Sabbath, right? You want to use Biot Sabbath. It's complicated, right? Okay. But you can use Faraday's law in this case. challenge you to try to do that. So you consider the same problem, it's smooth falling. You know the flux. The flux, so consider the loop falling exactly when it's at the surface of the solenoid. You can consider the solenoid to be of, the loop of to be of any radius r, right? Where r is less than a. Right? And it's just happened to be falling right there. It's on the logic. Okay? You know how to calculate the flux. Because the flux here is only dependent on the axial. Right? That is the only part that appears through the surface. The radial component is parallel to the surface, it doesn't contribute to the flux. So you can always calculate the flux anywhere there. Right? Right? And then you can mutual inductance whatnot. But I haven't really solved this, I just thought about it just now. But this is, at the end of the day, you can actually find the ratio between PR and DC by looking at this. So if I want to create an extra credit problem for that problem 637 or whatever, right, that would be calculating PR.
Is that not actually asked?
No. I'm just saying that you can calculate PR by Bayes-Sarbat law. Right, but Faraday's law also tells you something about it. See, I'm just saying that just like in thermodynamics, where everything seems circular, everything goes in a roundabout way. So it's electrostatic and magnetostatic and EMN in general. You can arrive at the same solution in many ways. Right? In fact, here there are two ways here. Right? I was looking at the potential, right? Or Faraday just look at the Einstein experiment. So, I just killed 3 minutes. Because the next thing is mutual inductance and self-inductance, and that will take the whole lecture of this Friday, and next week we'll talk about AC circuit.
Next Friday?
No, this Friday.
Okay.
This is Wednesday. Friday is inductance, and next week is AC circuit. And then there is a seminar at 4. You can should attend. It's exciting. It's about field field. So apparently you have aurora. If you're in Venus, right? In Venus you have aurora everywhere, right? Is that correct? Because there is enough of this cosmic ray from the sun, and then there is no magnetic field. So you see aurora. Is that right? You see aurora everywhere. But if on Earth, because of the magnetic field and charged particle, you get attracted to a because it's spiral around, just like what we talked about in lecture yesterday, right? Then you have aurora only in the near the north and southern pole of the magnetic field of Earth. How come you don't have aurora in the southern hemisphere? Is there aurora in the southern hemisphere? You do.
I think there should be.
In Australia? Or? Yes,
You probably see a little bit.
But in any case, there is a great lecture at 4. Abigail is hosting it. Oh, are you hosting it? I don't want to say that.
Well, the
but
SpaceX
you're part of the
legislative
audience, right?
Yeah.
And as a result, I might attend if I finish
I think Gary's
midterm grading.
Really? Yeah. He said he's
Otherwise,
For this? Is he in the region or what?